Hi students, in this video we are going to discuss the elementary transformations of a matrix. A matrix can be transformed to another matrix by certain operations called elementary row operations and elementary column operations. Let me see elementary row and column operations. Elementary row or column operations on a matrix are as follows. The first one, the interchanging of any two rows or columns of the matrix. Second one, replacing a row or column of the matrix by a non-zero scalar multiple of the row by a non-zero scalar. Third one, replacing a row or column of the matrix by a sum of the row or column with the non-zero scalar multiple of another row or column of the matrix. So next let me see example for the elementary row operations and the elementary column operations on a matrix are known as elementary transformations. We use the following notations for the elementary row operations. First one, interchanging of ith and jth rows is denoted by Ri interchanging Rj. Second one, the multiplication of each element of ith row by a non-zero constant lambda is denoted by Ri implies lambda into Ri. Third one, addition to ith row, a non-zero constant lambda multiple of jth row is denoted by Ri implies Ri plus lambda into Rj. Similar notations are used for elementary column operations also. Next, let me see the definition for equivalent matrix. Two matrices A and B of the same order are said to be equivalent to one another if one can be obtained from the other by the applications of elementary transformations. Symbolically, we write A equivalent to B to mean that the matrix A is equivalent to the matrix B. Next, let me discuss row echelon form. Using the row elementary transformations, we can transform a given non-zero matrix to a simplified form called a row echelon form. In a row echelon form, we may have rows all of whose entries are zero. Such rows are called zero rows. A non-zero row is one in which at least one of the entry is not zero. For instance, the matrix 6 0 minus 1 0 0 1 0 0 0, the first row and second row are non-zero rows, but third row is zero row. Definition for row echelon form: a non-zero matrix E said to be in a row echelon form if first one, all zero rows of E occur below every non-zero row of E. Second one, the first non-zero element in any row I of E occurs in the jth column of E. Then all other entries in the jth column of E below the first non-zero element of row I are zeros. Third one, the first non-zero entry in the ith row of E lies to the left of the first non-zero entry in I plus 1th row of E. For example, see the two matrices. Consider the matrix in first one. Go up row by row from the last row of the matrix The third row is 0 row. The first non-zero entry in the second row occurs in the third column and it lies to the right of the first non-zero entry in the first row, which occurs in the second column. So the matrix in row echelon form. Consider the matrix second one. Go up row by row. From the last row of the matrix, all the rows are non-zero rows. The first non-zero entry in the third row occurs in the fourth column and it occurs to the right of the first non-zero entry in the second row, which occurs in the third column. The first non-zero entry in the second row occurs in the third column and it occurs to the right of the first non-zero entry in the first row, which occurs in the first column. So the matrix is in row echelon form. The following matrices are not in row echelon form. You see the two matrices. Consider the matrix in first one. In this matrix, the first non-zero entry in the third row occurs in the second column and it is on the left of the first non-zero entry in the second row, which occurs in the third column. So the matrix is not in row echelon form. Consider the second one. In this matrix, the first non-zero entry in the second row occurs in the first column and it is on the left of the first non-zero entry in the first row, which occurs in the second column. So the matrix is not in row echelon form. Next, let me see rank of a matrix. To define the rank of a matrix, we have to know about submatrices and minors of a matrix. Let capital A be a given matrix. A matrix obtained by deleting some rows and some columns of A is called a submatrix of A. A matrix is a submatrix of itself because it is obtained by leaving zero number of rows and a zero number of columns. Recall the determinant of a square submatrix of a matrix is called the minor of the matrix. Okay, let me discuss the definition for the rank of the matrix. The rank of a matrix A is defined as the order of a highest order non-vanishing minor of the matrix A. It is denoted by the symbol row of A. The rank of a zero matrix is defined to be 0. That is, the rank of the null matrix is 0. Okay, let me see some note. So the first one, if a matrix contains at least one non-zero element, then rank of A is greater than or equal to 1. Second one, the rank of the identity matrix In is N. Third one, if the rank of a matrix A is R, then there exists at least one minor of A of order R which does not vanish, and every minor of A of order R plus 1 and higher order, if any, vanishes. Fourth one, if A is an M by N matrix, then row of A is less than or equal to minimum of M comma N. A square matrix A of order N has inverse if and only if row of A is equal to N. Let me discuss some theorems. The theorem 1.11 says the rank of a matrix in row echelon form is the number of non-zero rows in it. It means the rank of the matrix in row echelon form is nothing but the number of non-zero rows. How many number of non-zero rows are there? That is the rank of the matrix. So next theorem 1.12. The rank of a non-zero matrix is equal to the number of non-zero rows in a row echelon form of the matrix. So the rank of a non-zero matrix in the row echelon form, the number of non-zero rows. So next, elementary matrix. An elementary matrix is defined as a matrix which is obtained from an identity matrix by applying only one elementary transformations. So next, theorem 1.13, every non-singular matrix can be transformed to an identity matrix by a sequence of elementary row operations. For this theorem, we have one example, 1.19. Thank you, students.